Swayam Prabha. Digital India. Educated India.
Welcome to lecture 15 of the course on econometric methods for statisticians, data scientists and data engineers. The title of this lecture is specification analysis. While applying the multiple linear regression model in practice, it is very important to specify the model properly. Often you have a pool of explanatory variables and you have to select a subset of explanatory variables to be included in the model from that pool of explanatory variables. In such cases, it is always possible that you over specify the model or you have incomplete specification of the model. Means you leave some of the variables which should be included in the model, that is the case of incomplete specification, or you include some of the variables which are not so important for explaining why. This is excessive specification of the model. Now, if you face any of these problems, if you do not specify the set of explanatory variables properly, or if you exclude some of the relevant variables or include some of the irrelevant variables in the model, then it may adversely affect the properties of your estimators. It may also affect your test procedures as well as your forecasts. So, it is important to select the variables properly and it is also important to investigate the properties of the estimators when you have misspecified the model. Means you have either excessive specification or incomplete specification of the model. So, this is the objective of this lecture. We will consider the multiple linear regression model under two kinds of misspecification. When you have excluded some of the relevant variables, some of the variables which are important for explaining the variability of y, or you have included some of the irrelevant variables in the model, that is the variables which are not so important for explaining the variation in y. So, the specification of a linear regression model includes formulation of the regression relationships and assumptions concerning the explanatory variables and disturbances. In one of the lecture, we have considered the specification of disturbances. Say if you assume that the disturbances are spherical, but actually the disturbances are non-spherical, then how is it going to affect the properties of the OLS estimator and what are the options? Then you may misspecify the explanatory variables also to be included in the model, and any error in specifying these two is referred as misspecification error. Here specification error refers to misspecification in inclusion of explanatory variables in the model. So, you have misspecified the variables to be included in the model. So, suppose you have a pool of explanatory variables which possibly influence the process. And then you use a subset of explanatory variables in your regression. Actually, what is the purpose of these explanatory variables? The purpose of these explanatory variables is to explain the variation in y. So, while choosing a subset of explanatory variables from the pool of explanatory variables, you may make two kinds of mistakes, two kinds of specification errors. You may by mistake exclude some of the relevant variables, that is some of the variables which are actually important for explaining the variation in y, or you may include some of the variables which should not be there in the model, which are irrelevant, which are not able to explain the variation in y. Now, the process of selecting appropriate subset of variables is the process of variable selection. Of course, here I am not going to discuss the process of variable selection. My focus is on studying the properties of the estimator when you have misspecified the selected variables. Now, there are two possible options. Suppose you are selecting the variables from a pool of explanatory variables, then the two possibilities are: the analyst may include as many as possible explanatory variables to make the model as realistic as possible. The analyst is very enthusiastic and he has selected a large number of explanatory variables to be included in the model. And the second possibility is analyst may include only fewer number of explanatory variables to make the model as simple as possible. So, he is very selective. So, the two types of incorrect model misspecifications are, say, omission or exclusion of relevant variables. This is possible when the analyst is very selective about selecting the explanatory variables to be included in the model, or inclusion of irrelevant variables. And this may be possible when analyst includes a large number of explanatory variables in the model to make the model as realistic as possible. So, these are two model misspecifications or incorrect model specifications, which one may face. Now, first we consider the problem of exclusion of relevant variables. So, suppose some of the explanatory variables are excluded in the model, which are actually relevant in explaining the dependent variable. Explaining the dependent variable means explaining the variability of the dependent variable. So, these explanatory variables which are not included in the model, which are excluded from the model, have information about the dependent variable. So, definitely you are going to lose some information. And now, suppose there are k candidate explanatory variables, and out of those k candidate explanatory variables, r variables are included and k minus r variables are excluded from the model. So, all these k variables are important, all these k variables are relevant variables, but while specifying the model, you have not included k minus r variables. these k minus r variables are excluded from the model. So, you face the problem of exclusion of relevant variables. Now, we partition x as x 1, x 2, where this x 1 has r columns. So, this x 1 is a matrix of order n cross r, and x 2 is of order n cross k minus r. So, you have k minus r columns here in x 2. Again we partition beta as beta 1, beta 2, where again beta 1 has r elements and beta 2 has k minus r elements. Now, the full model or true model is y equal to x beta plus u, and then in terms of x 1, x 2, beta 1, beta 2, you can write actually x beta is equal to x 1, x 2, beta 1, beta 2. So, this is equal to x 1 beta 1 plus x 2 beta 2. So, you can write the model as y equal to x 1 beta 1 plus x 2 beta 2 plus u. Then you have excluded these k minus r explanatory variables x 2 from the model. So, the misspecified model after excluding these k minus r explanatory variables x 2 is y equal to x 1 beta 1 plus v. So, if we apply the method of least squares to this model 2, the misspecified model 2, then we obtain the OLS estimator of beta 1 as B 1 f equal to x 1 transpose x 1 inverse x 1 transpose y. So, this is the least square estimator of beta 1 based on this misspecified model. Now, suppose we write theta equal to x 1 transpose x 1 inverse x 1 transpose x 2 beta 2. Now, in this misspecified model, what is V? V is the disturbance term, and it includes x 2 beta 2 also. So, it is x 2 beta 2 plus u. Now, we obtain the bias and MSE of B 1 f. So, the bias and MSE of B 1 f are given by expectation of B 1 f minus beta 1 equal to x 1 transpose x 1 inverse x 1 transpose x 2 beta 2, which is equal to theta. We have denoted this quantity by theta. And then expectation of B 1 f minus beta 1 B 1 f minus beta 1 transpose is equal to sigma square u x 1 transpose x 1 inverse plus theta theta transpose. So, actually if we exclude some of the relevant variables, then your OLS estimator becomes biased, and this is the bias of OLS estimator. So, this is one of the adverse effect of excluding some of the relevant variables from the model. And then the MSE matrix is this. Actually, if you look at this part, this is the variance covariance matrix of OLS estimator B 1 f based on the misspecified model y equal to x 1 beta 1 plus v. And then you have this part also. This is because of the bias. To prove this result, we write B 1 f equal to x 1 transpose x 1 inverse x 1 transpose. Then we write y equal to x 1 beta 1 plus x 2 beta 2 plus u. Then the first term becomes x 1 transpose x 1 inverse x 1 transpose x 1, which is identity matrix. So, you get beta 1 here plus x 1 transpose x 1 inverse x 1 transpose x 2 beta 2, which we are denoting by theta. So, you get theta here plus x 1 transpose x 1 inverse x 1 transpose u, the last term. Now, if you take expectation, we take beta 1 towards the left hand side, then expectation of b 1 f minus beta 1 is equal to theta is equal to x 1 transpose x 1 inverse x 1 transpose x 2 beta 2. Now, this gives the equation 4 or result 4. Then the variance covariance matrix of B 1 f is expectation of B 1 f minus expectation of B 1 f, then B 1 f minus expectation B 1 f transpose. So, we obtain the variance covariance matrix of B 1 f. Now, expectation of B 1 f is equal to beta 1 plus theta. So, we get expectation of B 1 f minus theta minus beta 1 B 1 f minus theta minus beta 1 transpose. And then from here we obtain B 1 f minus beta 1 minus theta equal to x 1 transpose x 1 inverse x 1 transpose u. So, you get x 1 transpose x 1 inverse x 1 transpose u and then transpose of this. So, u transpose x 1 x 1 transpose x 1 inverse, and then we take expectation of u transpose. Expectation of u transpose is sigma square I n, then we take sigma square u outside. So, we obtain x 1 transpose x 1 inverse x 1 transpose x 1 x 1 transpose x 1 inverse. So, you get this final expression for the variance covariance matrix of B 1 f. Then we can easily obtain the MSE matrix. Actually, MSE matrix of B 1 f is equal to the variance covariance matrix of B 1 f plus bias of B 1 f and then bias of B 1 f transpose, and bias of B 1 f is theta. So, we obtain the MSE matrix as sigma square u x 1 transpose x 1 inverse plus theta theta transpose. Now, this gives you the equation 5, the expression for the MSE matrix of B 1 f. Then now we consider the expression for the error variance or the estimator of error variance sigma square u, and we are estimating sigma square u based on the misspecified model. So, suppose we denote the estimator by sigma head square u, then sigma head square u is equal to y minus x 1 B 1 f transpose y minus x 1 B 1 f divided by n minus r. Remember that in the misspecified model you have r number of explanatory variables. So, we divide by n minus r. Then we can write the numerator as y transpose m 1 y, where m 1 is equal to I n minus x 1 transpose x 1 inverse x 1 transpose. Now, we investigate how the model misspecification is going to affect the properties of this estimator. If we exclude some of the relevant variables, how is it going to affect the properties of sigma head square u. So, we obtain the bias of estimator sigma head square u, which is equal to expectation of sigma head square u minus sigma square u equal to beta 2 transpose x 2 transpose m 1 x 2 beta 2 divided by n minus r. Actually, we have m 1 y equal to m 1, we write y equal to x 1 beta 1 plus x 2 beta 2 plus u. Then this is equal to m 1 x 1 beta 1, but m 1 x 1 is equal to 0. This you can easily verify. So, the first term vanishes, then m 1 x 2 beta 2 you get here and m 1 u. So, y transpose m 1 y is equal to, again m 1 is an idempotent matrix and it is symmetric also. So, m 1 transpose is equal to m 1 and m 1 square is equal to m 1. So, you can write y transpose m 1 y as m 1 y transpose m 1 y, and then m 1 y is equal to m 1 x 2 beta 2 plus m 1 u transpose m 1 x 2 beta 2 plus m 1 u. So, you get this expression and then we simplify it. So, we get beta 2 transpose x 2 transpose, then you have m 1 transpose m 1 which is equal to m 1. X 2 beta 2. Then you get cross product term, the cross product term is u transpose m 1 transpose is equal to m 1, then m 1 you get here also x 2 beta 2, and you also get beta 2 transpose x 2 m 1, you can write m 1 square equal to m 1 here and u, and these two are equal. Actually, both are of order 1 cross 1, and if you take transpose of this you get this, and transpose of a scalar is the same scalar. So, actually you get 2 times beta 2 transpose x 2 transpose m 1 u here, and the last term is u transpose, then you have m 1 transpose m 1 which is equal to m 1 u. Then you can easily verify that expectation of beta 2 transpose x 2 transpose m 1 u is equal to 0, because expectation of u is 0. Then expectation of u transpose m 1 u is equal to n minus r sigma square u. So, we obtain expectation of y transpose m 1 y equal to beta 2 transpose x 2 transpose m 1 x 2 beta 2 plus n minus r sigma square u. Then sigma head square is equal to y transpose m 1 y divided by n minus r. So, if you take expectation of sigma head square u, it becomes beta 2 transpose x 2 transpose m 1 x 2 beta 2 divided by n minus r plus sigma square u. So, you get the expression given in equation 6. And from here we observe that sigma head square u overestimates sigma square u. In fact, this term gives you the bias of sigma head square u, and this term is greater than 0. Beta 2 transpose x 2 transpose m x 2 beta 2 is greater than or equal to 0. So, sigma hat square u overestimates sigma square u, the bias is positive. Thus, the t test for testing the significance of a single coefficient and f test for testing the significance of the entire regression will not be valid. In fact, both in t test and f test, you make use of sigma hat square u, the least square estimator of sigma square u. In fact, for testing the set of linear hypothesis r beta equal to small r, you also make use of this estimator sigma hat square u, the least square estimator of sigma square u. But this estimator is biased here, and if you look at the distribution of sigma hat square u divided by sigma square u, it is not the central chi-square distribution even under H naught, under the assumption of that r beta equal to small r. This does not follow central chi-square distribution, its distribution is non-central chi-square. So, the test is not valid. Similarly, the t test for testing the significance of a single coefficient or the f test for testing the significance of entire regression will not be valid. So, if you misspecify the model and if you exclude some of the relevant variables, then your tests will not be valid. Whether you are testing the significance of a single coefficient or you are testing the significance of entire regression or whether you are testing the equality of two coefficients or you are testing a set of linear hypothesis of the form r beta equal to small r, your test will not be valid. Now, we observe the effect of misspecifying the model on prediction. So, suppose the predicted value of y f corresponding to x f, where we write x f equal to x 1 f transpose x 2 f transpose, then transpose of this. So, actually you have partitioned x f as x 1 f, x 2 f. Then the predicted value based on the full model is y hat f equal to x f transpose b, where b is equal to x transpose x inverse x transpose y. And in the last lecture, we have also discussed that expectation of y hat f is equal to x f transpose beta, which is equal to expectation of y f, and variance of y hat f is equal to sigma square u 1 plus x f transpose x inverse x f. But here in the misspecified model, you are using just this set of variables for predicting y f. So, the predicted value based on the subset model is y hat 1 f equal to x 1 f transpose b 1 f. So, this is the predicted value based on the misspecified model. So, now we observe how is it going to affect the properties of this predictor, the model misspecification. The bias and MSE of y hat 1 f are given by expectation of y hat 1 f minus y f equal to x 1 f transpose theta minus x 2 f transpose beta 2, and expectation of y hat 1 f minus y f square is equal to sigma square u 1 plus x 1 f transpose x 1 transpose x 1 inverse x 1 f plus x 1 f transpose theta whole square plus x 2 f transpose beta 2 square. Actually, if you look at this expression carefully, then this part is because you are estimating or you are predicting y f based on x 1 f and b 1 f. So, if your model is a true model, means if your true model is y equal to x 1 beta 1 plus u, then the variance of predicted value is this. But since this is a misspecified model, you get this part also in the expression. So, the variance increases by this part. So, this part is because of misspecifying the model or because of excluding some of the relevant variables. Now, we have expectation of y hat 1 f equal to x 1 f transpose x 1 transpose x 1 inverse x 1 transpose expectation of y. We have just substituted the value of b 1 f, then we have taken the expectation, and expectation of y is equal to x 1 beta 1 plus x 2 beta 2. So, we get this expression for expectation of y hat 1 f, and then the first part is x 1 f transpose, you have x 1 transpose x 1 inverse x 1 transpose x 1. So, you get x 1 f transpose beta 1 here, x 1 f transpose beta 1, and suppose we add x 2 f transpose beta 2 also here, and then we subtract x 2 f transpose beta 2, and then this second part is equal to x 1 f transpose and x 1 transpose x 1 inverse x 1 transpose x 2 beta 2 is equal to theta. So, you get x 1 f transpose theta here. So, ultimately this is equal to x f transpose beta. So, you get x f transpose beta plus x 1 f transpose theta minus x 2 f transpose beta 2. Then, if you take expectation of y hat 1 f minus y f, you get x 1 f transpose theta minus x 2 f transpose beta 2, which gives you expression 8. So, this is the bias. Further, if we take expectation of y hat 1 f minus y f whole square, then this is equal to expectation of x 1 f transpose b 1 f minus x 1 f transpose beta 1 minus x 2 f transpose beta 2 minus u f whole square. Then actually this is the value of y hat 1 f, and then we have written y f equal to x 1 f transpose beta 1 plus x 2 f transpose beta 2 plus u f. So, we write this as expectation of x 1 f transpose b 1 f minus beta 1. We combine these two terms and then we take a square. So, we take a square of this plus x 2 f transpose beta 2 whole square plus expectation of u f square, and then you have we have this last cross product term also. Now, we can write the first term as x 1 f transpose, then in between we have the variance covariance matrix of, actually this is the MSE matrix of b 1 f, then x 1 f, and then we have x 2 f transpose beta 2 square plus sigma square u minus twice x 1 f transpose theta. This is actually the expectation of b 1 f minus beta 1, and then you have x 2 f transpose beta 2. And then we write the value of this expectation here, which is sigma square u 1 plus x 1 f transpose x 1 transpose x 1 inverse x 1 f plus x 1 f transpose theta whole square, and then we have this term here plus sigma square u we have already taken here, and then minus 2 times x 1 f transpose theta into x 2 f transpose beta 2. And finally, we get this expression. We combine these three expressions, and then we get x 1 f transpose theta minus x 2 f transpose beta 2 whole square. So, this gives you 9. Then we take the difference of MSE of y hat 1 f and variance of y hat f, and we obtain this expression for the difference. So, the variance of y hat 1 f or MSE of y hat 1 f actually increases by this factor. Now, we consider the case of inclusion of irrelevant variables. So, this is the true model, and the misspecified model is y equal to x beta plus z gamma plus v. Z is of order n cross r, and Z is the matrix of included irrelevant explanatory variables. Further, gamma is of order r cross 1. This is the vector of regression coefficients corresponding to the irrelevant explanatory variables. Then we apply OLS to this misspecified model too, and we obtain the OLS estimator as BF CF equal to, you have x z is your new explanatory variables matrix. So, x z transpose x z is equal to x transpose x, x transpose z, z transpose x, z transpose z. So, you get this matrix, and then x transpose y, z transpose y. And then from this equation we obtain x transpose x B f plus x transpose z C f equal to x transpose y, and z transpose x B f plus z transpose z C f equal to z transpose y. B f and C f are the OLS estimators of beta and gamma for the misspecified model. Then we pre-multiply equation 4 by x transpose z, z transpose z inverse. So, we obtain this equation x transpose z, z transpose z inverse, z transpose x B f plus x transpose z C f equal to this part. Then we subtract equation 5 from 3. So, this second term cancels out, and we obtain this equation just simply by subtracting 5 from 3. And from here you can obtain the value of B f. We write m z equal to this matrix I minus z, z transpose z inverse z transpose. So, you get x transpose m z x B f equal to x transpose m z y, and so B f is equal to x transpose m z x inverse x transpose m z y. And then we substitute the value of B f in equation 4. We substitute the value of B f here, and then we solve it for C f. So, finally, we obtain the expression for C f equal to z transpose z inverse z transpose y minus x B f. Then the variance covariance matrix of B f is equal to expectation of B f minus beta transpose. Then we substitute the value of B f minus beta from here. So, we substitute B f minus beta equal to this, and then we obtain x transpose m z x inverse x transpose m z, expectation of u transpose m z x x transpose m z x inverse. Then expectation of u transpose is sigma square u I n. So, finally, we obtain expectation, finally, we obtain x transpose m z x inverse here. So, this is the variance covariance matrix of B f. Then for the true model one, the OLS estimator of beta is B equal to x transpose x inverse x transpose y, and this is the variance covariance matrix of B. And if we take the difference variance of BF, which is the variance covariance matrix of the estimator for the misspecified model minus variance covariance matrix of B, then we obtain sigma square u x transpose m z x inverse minus x transpose x inverse. Now, to observe whether this difference is positive definite or not, we again make use of this result, which we have already proved earlier. So, for two positive definite matrices A and B, A minus B is at least positive semi definite if B minus B inverse minus A inverse is at least positive semi definite. So, we take the difference x transpose x minus x transpose m z x, and this is actually equal to m z is equal to I minus z, z transpose z inverse z transpose. So, finally, you get x transpose z, z transpose z inverse z transpose x. Now, this matrix is at least positive semi definite, and this implies that the difference between the variance covariance matrices of B f and B is at least positive semi definite. So, if we use the misspecified model and if we include some irrelevant variables in the model, it is going to decline the efficiency of the estimator. However, if z transpose x is equal to 0, that is x and z are orthogonal to each other, then B f and B are identical to each other. This you can easily verify. Actually, the expression for B f is this, and if x is orthogonal to z, then this simply reduces to x transpose x inverse x transpose y, because in that case x transpose z is equal to 0. Then we consider the OLS estimator of gamma, which is C f. We can write C f as z transpose z inverse z transpose I minus x, x transpose m z x inverse x transpose m z y. And then this is equal to z transpose z inverse z transpose m z x y, where m z x is equal to I minus x, x transpose m z x inverse x transpose m z. Again, you can easily verify that m z x is idempotent. If you take a square of m z x, then it is equal to m z x. Then the OLS residual for the model 2 is E f equal to y minus x B f minus z C f. This is the OLS residual for the misspecified model. And then this is equal to, we have y here and then x times B f. B f is equal to x transpose m z x inverse x transpose m z y. So, we take y common here, we get this matrix here, and then z times C f. C f is equal to z transpose z inverse z transpose m z x y. So, you get this term here, and then you can write it as this term is equal to m z x. This gives you m z x minus I minus m z x y, and then this m z x gets cancelled. Actually, I minus m z is equal to z z transpose z inverse z transpose. So, we have replaced this z transpose z inverse z transpose by I minus m z. So, finally, you get m z x y, and we write it equal to m star z x y, where m star z x is equal to m z x. Then the residual sum of squares is E f transpose E f, which is equal to y transpose m z x star y. where mzx star transpose mzx star is equal to mzx star. So, we have used this result and then we get this expression for EF transpose EF. Further, if we take trace of mzx star, then this is equal to trace of mz minus trace of mzx x transpose mzx inverse x transpose mz. Then what we do? Trace of mz is actually n minus r, and then we obtain the trace of this second term. You get trace of x transpose mz x inverse. We take this mz towards the end. So, you get x transpose mz square is equal to mz, and then we also take this x towards this side. So, you get an identity matrix of order k, and trace of this identity matrix is equal to k. So, you get this term. So, expectation of RSS is equal to sigma square u trace of mzx star, which is equal to sigma square u n minus k minus r, or expectation of RSS upon n minus k minus r is equal to sigma square u. So, this gives you an unbiased estimator for sigma square u. RSS upon n minus k minus r gives you an unbiased estimator of sigma square u. So, we have considered both the cases when we have excluded some of the relevant variables or when we have included some of the irrelevant variables in your model. So, in this table we have summarized our results. Say, suppose you are excluding the relevant variables, then estimator of regression coefficient, we have shown that the estimator of regression coefficient vector becomes biased. But in case of misspecification of inclusion of irrelevant variables, it does not become biased, it still remains unbiased. Then the efficiency of the estimator, it declines in both the cases, when we exclude the relevant variables or when we include the irrelevant variables. In both the cases, it declines. Then estimation of the disturbances variance. In case of exclusion of relevant variables, we have observed that the bias is positive. So, it overestimates the disturbances variance, whereas in case of inclusion of irrelevant variables, it remains unbiased. Then, if we use the testing of hypothesis or confidence intervals, like if we consider the test of the significance of a single regression coefficient of or test of the entire regression or test of any linear hypothesis, then for the case of exclusion of relevant variables, the tests are invalid and faulty inferences are drawn, because the distribution of test statistic does not remain central f, and the reason is the distribution of s square upon sigma square u does not remain central chi square even under h naught. For the second case, inclusion of irrelevant variables, it still remains valid, but you usually get error in your final findings. So, you get erroneous results. So, in this lecture we have considered the problem of incomplete specification of the model or over specification of the model. We have observed that if we by mistake exclude some of the relevant variables or if we include some of the irrelevant variables, it adversely affects the properties of the OLS estimator of regression parameters. Not only that, it also affects the properties of the estimator of disturbances variance. In fact, for the case of under specification of the model means when you leave some of the relevant variables, the distribution of S square upon sigma square u does not remain central chi-square. So, you cannot even apply the tests for testing the significance of the regression or for testing the significance of a single coefficient. Then we have also observed the effect of misspecifying the model on the prediction. We have observed that it adversely affects the predictions also. So, here I am going to stop. Thank you.
Hi, I am Chitwan Lalji, a PhD student of Health Economics under the supervision of Dr. Debyan Pakrashi from the Department of Humanities and Social Sciences, IIT Kanpur. In one of my essays, I am interested in understanding the relationship between consumption of fruits and vegetables and various health indicators. Health indicators, both subjective and objective health indicators like mental health, self-assessed health, various measures of blood pressure and various measures of cholesterol. Measures of blood pressure like systolic and diastolic BP, you have your incidence of high BP, MAP and incidence of high MAP. And as far as cholesterol is concerned, I have tried to concentrate more on total cholesterol, good cholesterol and incidence of high cholesterol. Now, before I go on to what have been my major contributions and various policy implications, I would like to briefly tell you about the policy initiatives of WHO and various countries. The WHO, that is the World Health Organization, it started with a campaign of 5 a day. That is, you should have 5 portions of fruits and vegetables per day. That would be approximately, you could say, 400 grams of fruits and vegetables. Now, a portion, before we go further, I'll just tell you what exactly is a portion. One portion is equivalent to a medium-sized apple, or one small glass of fruit juice, which is approximately 150 milliliters, and maybe 3 teaspoons of vegetables. So, the WHO went with a 5 a day campaign, which was further taken up by various countries. Countries like UK, Netherlands, Germany, Norway, they adopted the 5 a day policy, while some went for expansionary dietary policies like France, Australia, Canada, Denmark. So, for example, Australia, it went for go for 2+5 policy, in which it said that you should consume 2 portions of fruits and 5 portions of vegetables per day. And USA went for a policy of fruits and vegetables more matters. That is, you must consume more and more fruits and vegetables. Now, irrespective of these expansionary dietary policies and dietary propagations, it has been found that only 28% of women and 25% of men, they actually meet the recommended dietary norms of 5 a day portion. So, the major contribution of my work is firstly to find an association between fruits and vegetables, whether there exists a relationship between fruits and vegetables and health indicators, and if they exist, whether due to heterogeneity in the data. So, I will be doing it according to age, by gender and by your weight. So, apart from that, I will go for policy recommendations, in which I am basically studying how much fruits and vegetables matter. Apart from that, which type matters more. So, for that I have taken data from the Health Survey of England. Health Survey of England is an annual survey which takes data, which conducts information regularly on demographic and socioeconomic characteristics. You have your lifestyle behaviors like an individual smokes or doesn't smoke, alcohol consumption, you have your sedentary and physical activities, and you have various health indicators also which have been collected. Before I go on to what exactly is my research, I would like to concentrate more on fruits and vegetables, like what kind of questions were asked in the survey. Questions like, what kind of fresh fruit do you eat? Did you eat any dried fruit yesterday? Don't count dried fruits in cereals, cakes. Apart from that, for vegetables, they asked how many tablespoons of vegetables did you eat yesterday? So, approximately after this whole survey was conducted, data was converted into portions of fruits, and like for example, 3 tablespoons of vegetables is equivalent to 1 portion. So, data was converted and provided to the users, that is us, from the UK Data Health Survey. So, the major contributions of my paper is that I found a strong negative association between intake of fruits and self-assessed health, then various measures of blood pressure like mean arterial pressure, high blood pressure, systolic and diastolic BP, and your total cholesterol. Apart from that, I have found a strong positive association between consumption of vegetables and good cholesterol. So, it is recommended in a way that if you want to control your blood pressure, you must consume more and more fruits. And as far as vegetables are concerned, they impact your good cholesterol. Apart from that, I went in for a falsification test. A falsification test is basically conducted to know whether the model that you have adopted and the conclusions that you are drawing are not spurious. So, if a falsification test is done to know, in a way it is tested by seeing an indicator, a health indicator which is not being impacted by your consumption of fruits and vegetables, and then we see whether there is significant result or not. If there is no significant result, that means your model is good and your results are non-spurious. So, what we did is, for falsification test, we took ear complaints and infectious diseases. Now, ear complaints like if you are deaf since birth or you have some kind of imbalance, body imbalance, that is not being impacted by your consumption of fruits and vegetables, and we did find insignificant results. Apart from that, infectious diseases like HIV, AIDS, etc., we found similar insignificant results, indicating that our results are non-spurious. Apart from that, we went, since there was a lot of heterogeneity in the data, like by gender, by age and by weight, we did the regression analysis. We found results which stated that as far as fruits are concerned, it impacts a male's health more than a female's health. So, it is basically said a man should consume more fruits to impact his health, whereas as far as vegetables are concerned, they impact a women's health more. But this has been only seen as far as cholesterol is concerned, the various measures of cholesterol like total cholesterol, good cholesterol and your incidence of getting high cholesterol. Now, after this we went in for a policy implication, and in the policy implication we tried to find 2 policy implications, what matters and exactly how much portion matters. So, as far as how much portion matters, we have found that on an average 5 or more portions of fruits impact your overall health, that is your self-assessed health, your MAP, your incidence of high MAP and incidence of high BP. But if you want to have a good mental health, so you can optimize your mental health by consuming 3 or 4 portions of fruits as well. And similarly, as far as self-assessed health and total cholesterol is concerned, an individual must consume 4 to 5 portions to optimally have the impact of consumption of fruits. Apart from that, vegetables have had a very little impact on your health. It only impacts your incidence of getting high MAP and high BP, and it's seen that only it impacts when you consume 5 or more portions of fruits. So, an optimum consumption of 5 or more portions of fruits and vegetables are recommended, but fruits have a more impact on your overall health, on various measures like self-assessed health, mental health, your various measures of blood pressure and various cholesterol levels. Another thing that we find is which type of fruit matters. It has been seen that all size fruits, they impact your self-assessed health, your systolic and diastolic blood pressure, your mean arterial pressure, your high BP and incidence of getting high MAP and high cholesterol. But we find that as far as frozen fruits or canned fruits are concerned, they help in regulating your incidence of getting high MAP or high BP, but it has a trade-off. That means there is something negative happening. It reduces the good cholesterol in your body. Apart from this, if you have an incidence of getting high cholesterol, it is recommended that you must consume fruit juices because it has a impact in reducing your probability of getting high cholesterol. And dried fruits, they impact your self-assessed health. As far as vegetables are concerned, very little impact has been seen. It has only been seen in case of portion of salads and its association with self-assessed health. Another thing that they have seen is vegetables in composite, they have an association with good cholesterol. So overall, my research basically says that there is an association between consumption of fruits and vegetables and various health indicators, and it is highly recommended that an individual, in order to be healthy, must consume 5 or more portions of fruits and 5 or more portions of vegetables per day, but fruits have a more impact on your overall health. Apart from that, all size fruits, they have a better impact on your overall health, your mental health, various measures of blood pressure and cholesterol. So, thank you.